Okay. As I mentioned earlier, this is week number 4, and the big topic that we try to discuss here is about measurement uncertainty. And this week we are focusing on the source of systematic error. And in this topic, we have calculations and also some definition of source of systematic error. Okay, about the content, in if you have a look at chapter 3, Reza Langari book, I also uploaded in our e-learning. You should download it and try to read it later on. For the source of systematic error, we have 4 over here. The first one is system disturbance due to measurement. Normally due to our instrument itself, for example, voltmeter, ammeter, where you know that in our instrument, for instance, let's say a voltmeter, we do have an internal resistance of the instrument itself, measuring instrument itself. So the internal resistance of the voltmeter should be properly designed, for example, selected or designed in order for us to get the true measurement of our, for example, if we try to measure voltage in our circuit, so the not only our circuit should be should be energized or should have some components in there. Our instrument also need to be calibrated or need to be suitable enough in order for us to mitigate or reduce the system disturbance. And the second one is on the error due to environmental input. And environmental input, as we previously learned, that there are 2 important issues that will raise from this environmental input. The first one is zero drift. The second one is sensitivity drift. So if systematic error due to this environmental input, what we're trying to do is we try to suit our application. For example, we try to use it in a proper environment. And the third one is where in instrument components. So if we use the instrument for quite a long time, maybe we need to recalibrate the instrument, or maybe we need to replace some of the components. For example, if the instrument itself consists of spring elasticity, the performance of elasticity has been reduced, so we need to replace that one as well. Sometimes in our digital multimeter, for example, we need to replace the battery because the battery in somehow have no voltage or no current, no energy inside the voltage. So no energy inside our battery. So we need to replace that one in order for us to get energized back our instrument and try to measure, use our instrument in measuring. And also the connecting leads. Connecting leads is basically related to resistance value of our probe. All right. If we look at in general, basically measurement uncertainty, we have 2 portions over here. The first one is systematic error, and the second one is known as random error. And here is the definition of both systematic error and as well as random error. For today's class, I think we focus on the left hand side where it is systematic error. and maybe next week we'll have a look at a random error, continue towards random error. Okay, the definition of systematic error. This is an error in the output reading of measurement system that are consistently on one side of the correct reading. So that's the definition of systematic error. On the other hand, for random error, it is random, unpredictable perturbation effects of measurement either side of the true value. So it can be positive value, it can be a negative value. So random error is something which is unpredictable. And for the source of systematic error, normally it's due to system disturbance during the measurement, maybe due to our instrument itself, um, whether the internal resistance, maybe the wearing issue, maybe sometimes the lead value or lead effect, and also not to forget is maybe sometimes due to effect of environmental changes. So the surrounding, the ambient condition of our environment. And for random error, the source is interpolation that involve human observation, and also due to electrical noise. We know that noise is very random and also unpredictable. So this is sort of um, source for both for systematic error and random error in general. Okay, if we get into details, I think we discussed this bit, sources of systematic error. We know that we have effect of environmental disturbance, known as modifying input, also known as modifying input, basically due to internal resistance of our measuring instrument, and also disturbance of measured system by the act of measurement. And the act of measurement, maybe we try to measure, use our instrument in the condition or in the environment which is not suitable for the measurement. And the third one is changes in characteristic due to wear in instrument component over a period of time. So I've also explained about this, maybe due to the spring of the deflection spring, maybe due to the power source of the instrument, battery, you need to replace it over time. And also resistance of connecting leads, the probe itself, the resistance of your probe. That also might be one of the factor, one of the sources of systematic error. Okay, we have a look at the calculations of how do we, in this case, we have a circuit. We try to measure a circuit using a voltmeter. So this is considered system disturbance due to our measurement instrument. So here, if we read through, the process of measurement always disturb the system being measured. The magnitude of disturbance varies from one measurement system to the next, and if affected particularly, is affected particularly by the type of instrument used for measurement. Way of minimizing disturbance of measured system are important consideration in instrument design. Let's say we take an example of this circuit, and we try to measure resistance. For example, in this case, we try to measure the voltage across R5 or 1000 ohm resistor. So suppose we have these two circuit arrangement. The first on your left hand side is the circuit itself. On the right is our measuring instrument or our voltmeter. And in voltmeter, normally we have a deflection module. Normally we have a galvanometer over here. Deflect, maybe this is considered as analog multimeter. Or if we have digital multimeter, also we can represent the deflection of the value that we measure, the variation of the measured value by this circle with arrow, pointing arrow. And also we have RM. RM is basically internal resistance of our meter or of our instrument. And the thing that I mentioned before this is that this RM need to be properly selected or need to be properly the value of RM need to be properly selected lah. In other words, if RM value is not properly selected, it might affect the value that we try to measure for voltage across R5. Okay, the question over here says that suppose that the component of the circuit shown in figure 3.1a have the following values. We have R1 400 ohm, R2 600 ohm, R3 1000, R4 500 ohm, and R5 is 1000 ohm. And the voltage across AB is measured by a voltmeter whose internal resistance RM, I mentioned earlier, is 9500 ohm, 9.5 kilo ohm. What is the measurement error caused by the resistance of the measuring instrument? So in this case, we have all the values of resistors, and we also know that the internal resistance of or RM for the voltmeter is 9.5 kilo ohm. So here we try to measure the voltage across AB and try to identify what is the measurement error or what is the difference between theoretical value of voltage across AB and also the one represented by the voltmeter or measured by the voltmeter. So how do we calculate this one? So to calculate that one, I think all of you who are now in semester 2 already took fundamental of electrical circuit in semester 1, and for those who are get the exemption for fundamental, maybe have learned about circuit analysis in your previous institution. So here we try to apply what we learned last semester, which is Thevenin theorem, in order to represent or in order to simplify this complex circuit, consider a complex circuit, to be represented as a circuit which consists of equivalent resistance and also equivalent voltage source. So if we look at Thevenin theorem, what we will have is we will have a voltage source which is in series with this resistance RAB. So now the issue of trying to get what is the measurement error, we have two issues over here. First one is how do we simplify that circuit? The second one is what kind of calculation that we need in order to determine the measurement error. So here, let's say we done with the Thevenin theorem and so on. If you look at the circuit that we have over here, if you try to find what is the Thevenin equivalent circuit of this complex circuit, what you're trying to do first is for all voltage source, you need to make it as a short circuit. So we have two voltage source over here, E1 and E2. Both E1 and E2 should be short-circuited. And you try to find what is the resistance looking from terminal A and B. Later on, I think I will explain details step by step on how do we get the RTH and later on calculate the measurement error. At the moment, please, once we have the Thevenin equivalent resistance, so we do have this value now. And what we're trying to do is we try to find what is the ratio between voltage, looking at the our instrument, and also the open circuit voltage EO over here. Basically, um, if we did not connect our instrument to the circuit, this EO will be our open circuit voltage. You know that if open circuit voltage is basically the same as the voltage ES over here. So here we will try to take the ratio between EM and EO, and from the ratio we know that the measurement error only related to the value of resistors that we have in the circuit. We have two resistors over here. We have RAB and RM. So the influence of error basically due to this RM divided by RAB plus RM resistor. So here we know that for measurement error, we just minus the EO or the open circuit voltage, and also the measured voltage by the instrument if the instrument is connected. So if you look at this equation, EM over EO, basically it's coming from the equation of current when we try to connect this instrument to our circuit. It's okay. Later on, I will give you guys another solution. I mean, another file, PDF file, where I explain one by one how does this equation, how do we get this equation. And at the moment, we know that the measurement error is given by this EO minus EM, and we try to substitute, or we try to represent this equation in terms of EO. So now here we have the difference is EO times 1 minus RM over RAB plus RM. And if you substitute all the values of resistors, you might find that the difference here, EO minus EM, is 0.05 EO. Means that this 0.05 is our error over here. And if you look at our calculation, we don't have to calculate what is the value of EO as well as ES. Only find the value of RTH. Why? Because this value could be any value. The one that we interested is what is the difference? What is the factor of the difference? So here we have 0.05. If we convert it into a percentage value, the percentage error in the measurement is about 5%, or this 5% is basically represent the loading effect of the measuring instrument. In other words, what we're trying to get over here is that, let's say EO is 10 volts. Okay, the value that we measure, that we get from our voltmeter, most probably is 9.5 volts because of this 5% of error measurement in our error in our measurement. Okay, maybe you might find this is something quite blur in terms of the calculation. So we have a look at this file. So here I have step by step, not step by step lah, but a more detailed explanation on how we get our 5% of measurement error. Okay, let's say this is the circuit. We have the circuit and we have the terminal over here, A and B. When we try to connect our voltmeter, so here is our RM, consider as a shunt resistor. if you read through Reza Langaribu, our reference textbook, RM also known as shunt resistor, and the idea of selecting the value of shunt resistor is that we try to make the RM value as high as possible in order for us to get the same value that we calculated using a theoretical approach. So here, the difficult part is try to find RTH. So as I mentioned earlier, this is our circuit and this is our open terminal, and we try to find RTH from looking from this side, and we have we have E1 and E2 considered as a short circuit. This is part of the strategy of finding RTH. So now we have these two short circuit, and we try to find RTH over here, and this is the open terminal. So if you look step-by-step calculation over here, first I solve these two and put it as RA, and later on this RA combined with R3 and become RB, and later on RB combined with R4, it became RC, and for the total resistance, or sorry, the Thevenin resistance is basically RC in parallel with R5, and finally we get what is the value of our Thevenin equivalent resistance, which is 500 ohm. All right. According to the in terms of finding the measurement error, so first, if we look over here, here are the definition of what we have in this circuit. The first one, RTH, is basically RAB over here, and we put it as combine it with ES to complete our Thevenin equivalent circuit. And EO is basically the open circuit voltage, and this is a terminal A and B as we mentioned earlier. So, and if this is open circuit, means that the voltage that we find over here, EO, is the same voltage that we have over here, ES. And EM is basically the voltage measured by the instrument or by our voltmeter. Let's say if we connect this terminal, this AB terminal with our equipment or our voltmeter, and we might find that there is a current flowing in the circuit, and the current can be defined as this equation, I equals to ES or EO divided by the combination of these two resistors. And we know that EM is basically voltage across A and B. So voltage across A and B is basically coming from RM divided by RA plus RM times EO, or this value ES, our Thevenin voltage value. And this is by this equation is basically coming from voltage divider. The first one is just a simple Ohm's law. The second one is from the voltage divider. And from this voltage divider equation, or from EM equals to RM divided by RAB plus RM times EO, we know that if we bring EO to the left-hand side, we might find the ratio of our that leads towards the measurement error value. So now here, if looking at the ratio, if we try to put if we try to design RM as high as possible, we might find the ratio will become 1, meaning that whatever value that we calculated in theoretical will be the same value that appears in our voltmeter. So RM should be designed as high as possible. Let's say if we design RM is infinity, so infinity divided by infinity, it will become 1. And we know that EM and EO it's identical. So whatever we try to calculate using theoretical and whatever appears in our voltmeter will be identical as well. So that's why we need to select higher value of Rm in this case. But in our question previously, we know that Rm have been selected as 9.5 kilo ohm. So from that value, we know that EO will be, the difference between EO and EM, EO minus EM is given by this equation or given by EO times 0.05. And we know that this 0.05 is basically our measurement error. If we put it in percentage, it is 5% value. Or maybe you can also not necessarily using this equation. Maybe you can also use this equation as well. You can use E EM maybe I put it here, easier. Okay, maybe from that equation, where's my pen? Okay. All right. Okay, what you can do is that from this equation, basically you can also know or you can also predict what is your measurement error. For instance, let's say from this equation we have EM. If we bring EO to the right hand side, we have EM equals to RM divided by RAB plus RM times EO. Okay. If we put numbers or if you put the value of resistor that we have RM, which is 9.5 kilo, and we have RAB is given by 500 ohm. You might find that at the end you have EM is equals to 0.95 EO. Okay. This will explain to us that our measurement or the voltage appears in our voltmeter is slightly less than what we have from our theoretical value, which is EO over here. Suppose that if we have EO value of 10, means that the value appears in our voltmeter is about 9.5 volts. So 9.5 volt, if you compare with our nominal 10 volt, it's about 5% of error. So that's how we assess the measurement error. Either by using this equation, you can also find this 5%, or you can also use the definition of EM over here, or the equation of EM over here. And which one that you prefer, I didn't, I keep it as option for you guys. If you try to calculate the measurement error using this approach also can. If you try to use this approach also can. But at the end, in order to state the value of measurement error, you should always get the same value whether using this approach or using this approach. Is it okay?
Yes, doctor.
Is it clear? Okay, later on I will put this solution in e-learning. You can also download it from e-learning as well. At the moment, we don't have it in e-learning yet. All right. So that's for the calculations part. And as I mentioned earlier, if we think about environmental is the issue over here, is the concern. So the error due to environmental input only uh, leads towards sensitivity drift and also zero drift. So now what system designer can do is that try to reduce the vulnerability of measuring instrument to environmental inputs, or sometimes maybe we can quantify, and we quantify and then try to compare with nominal value of the measurement. So that's how we um, like compensate the environmental influence of environment. So, it's true that in any general measurement situation, it's very difficult to avoid because it's due to the nature. So what we can do is we try to reduce it by put it in a different place or put it in a proper place or of measurement, or sometimes we try to quantify and we try to predict in advance what um, how to compensate the issue of sensitivity and also zero drift error. Okay, the next one is where in instrument component. I think I've explained previously in our lesson. The issue here is that how do we overcome this wearing issue? So how do we overcome? Normally we try to calibrate our measuring instrument over the time. So for example, if you use meter and multimeter, for sometimes one at a time we need to calibrate back the zero pointing zero value of it. Maybe we try to change our battery of our multimeter, something sort of try to refresh back our measuring instrument. Okay, and the last one is connecting leads. And the issue here is that the resistance of our probe. So the choice of probe is also significant, but not, this is something which is um, not as significant as what we seen earlier. But it is also one of the factor. So the consideration of selecting your probe is also crucial. So you need to know what is the cross section size, how the cable, the root of the cable, as well as um, maybe the type of the your probe itself. And issue that may arise here is that it may introduce noise. Okay, if you don't properly choose your connecting leads. But normally you might say that this is already being handled by the manufacturer. Yes, it is true. But if you are the manufacturer, or if you try to develop your system as a designer, so this is also part of um, consideration or concern that you need to pay attention with. Then the issue here is the noise, as I mentioned earlier. And I think that's all for today. And we put it into summary. In summary, we have, if we talk about systematic error, we have four elements over here, or four sources system disturbance due to the internal resistance of our instrument itself. Okay, I also show you the calculation, how to calculate, and remember that you need to revise back how to simplify your circuit. In other words, you need to know how to analyze your circuit using a Thevenin equivalent circuit. And if you look at the example that I showed earlier, we don't have to calculate what is the value of EO, ES, as well as EM, because that one, the value of that particular part is not related if we, as far as measurement error um, is concerned. So the most important thing is the design of our measuring instrument. The resistance, internal resistance of our measuring instrument itself is the most important factor that will affect the loading effect or the error of our measurement. The second one is environmental issue. I think this is we cannot do anything about the error unless we try to find a suitable error. Suitable environment for our measuring strategy, and also maybe we try to compensate. We try to calculate our the error due to the environment, for example, zero drift and also sensitivity drift, and try to compensate back to know what is actually our true value that we are trying to measure. The third and the fourth one is due to wear and tear. We need to recalibrate our instrument. And finally, the connecting leads is not some, I would say it's not like something we as a user would know a lot, but if you are a designer, you need to think about what is the suitable connecting lead for, or to reduce the noise of your measurement. All right, I think that's all for today. You have any question?
So far, so good, Doctor.
Yeah, so far so good. That's why I,
Doctor,
yes,
I have question, but not regarding our lesson today. It's about the assignment yang report hari tu.
yes, okay.
Okay. For the report, do we have to provide a circuit, schematic circuit for it, or we just write a research?
You don't have to design the circuit for you for in the report and present it in the report. What you need to do is you need to suggest these are the suitable instrument that we will use in order to measure our concern. Two modules, I believe. One is the pedal position, and also another one, is it PIP? I didn't remember. But you don't have to provide the circuit. You just suggest your instrument, and maybe you might also suggest where to put and how to put how it's operate like. For example, if you try to for the pedal position, so maybe you put some sketch of the pedal and where to put the instrument, or where to put the sensor to measure the angle of pedal position. Is it okay?
Okay, doctor. Got it.
Just
Thank you.
just a sketch, not a proper, let's say, not the working circuit lah, complete circuit. All right.
Okay.
Okay, thank you. Right. If you look at e-learning, as I mentioned earlier in the class, I provided a homework where you need to finish your homework by Sunday. Sunday means that you need to submit all your the solution lah. But on Thursday, okay, for those who finish their solution or already got the answer, maybe you can share your answer during our tutorial session, and we try to discuss and try to determine whether you made mistakes or how can you improve your answer. So, is it okay?
Okay, Doctor, clear.
Okay, Doctor. Okay, Doctor.
All right. Anyway, I try to stop the recording now.